Make an immediate instant contact.
With this topic, yeah. All right, thank you. We'll be here more than 1 hour if I'm going to tell you everything. All right, so first of all, I'd like to thank the organizers for the opportunity to speak here. I feel obliged to apologize that my talk will not contain any non-commutative geometry at all. But maybe at the end of it, you might see a non-commutative version of this story. So hopefully this will inspire some of you at least. So the idea is this notion of contact instantons. Should I start over? Oh, well, I haven't got to that yet. You weren't that late. The idea is that this fits in within a larger program initiated by Donaldson and Thomas in 1998. So most of you probably know about instantons. I'll give you a definition, but the idea is that the moduli space of instantons is a very rich geometric object, and in the hands of Donaldson, it was used to understand four manifolds. So it's spectacular results in the 80s about smooth structure on four manifolds. Now, in high dimensions, of course, we know much more about smooth structure. So the question is why you would be interested in high-dimensional instantons. And I guess one motivation would be that the idea is that if you can construct invariants, then you should be able to get invariants for or abstraction for these sort of geometric structures. So it's less about the actual manifold itself, the topological structure, but it's more about the geometric structure you could put on manifolds. All right, so let's get started. My spaces are all nice commutative manifolds. So if you start with an oriented Riemannian n manifold, and if you have a 4 minus n form on your manifold, then we say that a connection A on some G bundle on a manifold is an omega instanton if it satisfies something that looks very similar to the usual instanton equation. So is and no, this is n-dimensional manifold. And of course, yeah, it's a minus sign. N minus 4. All right, that makes more sense. Instanton. Yeah, sorry, you're going to see a lot of these errors because I'm extremely jet lagged. I've been up since 1 a.m. So yeah, keep an eye open for stupid stuff. So is an omega instanton if the curvature satisfies the following equation. So you have a Riemannian manifold, you have a Hodge star operator, and now this gives you it's a 2 form, so it gives you n minus 2 form, and then you can make sense of this equation on not just a 4 manifold, but in higher dimensions. Sorry? Oh no, so I'm getting to that. No, so you don't need that. So well, it depends what you're after. But so if you use the Bianchi identity, if you differentiate this, well, you see that you don't get, in general, you don't get the Young-Mills equation, but you get this would be equal to 0, would be the ordinary Young-Mills, but you get this extra term. So of course, if the form is closed, then such an instanton will be a Young-Mills instanton. But in general, it won't be. So in the case where omega is a closed form, that was studied by Tien in I think it's year 2000. So he formulated a theory for moduli space of such instantons. But you don't need. So if you don't assume that this form is closed, you get some surprising situations where this such an omega connection is still a Young-Mills connection. So for some reason, this might vanish under some conditions. So I'll give you some examples. Let me just, before moving on to the contact ones, let me just give you a few instances of such high-dimensional instantons. So example. So number one is just if you're in a 4 manifold, then you just pick your omega to be plus or minus 1 on an oriented 4 manifold. And that gives you the usual instantons on a Riemannian oriented 4 manifold. And in fact, in this case, the important difference is that on an oriented manifold, you can just flip the orientation. And so essentially, the self-dual and anti-self-dual, depending on the sign here, gives you essentially the same theory, still relevant. We see that that's actually quite different when you go to higher dimensions. So another example is Hermitian-Einstein. Connections on a 2m dimensional Kähler manifold. So in that case, you pick omega to be 1 over minus 2 factorial and n minus second power of your Kähler form. So on 2m dimensional Kähler. All right, moving on, and then two more examples that actually have been studied quite a lot by, in particular, Donaldson's own students, but other people. That's the case of G2 instanton on a 7 manifold. So in that case, there's a distinguished 3 form on a G2 manifold preserved by the holonomy group G2. So you pick omega to be your 3 form. And finally, is the most exceptional holonomy is spin 7 instantons on an 8 manifold, where you pick this phi omega to be the 4 form on your 8 manifold that's preserved under spin 7. So you see that this equation is really subsuming a lot of special cases, and this talk is about one more case. So 5 is the notion of a contact instanton. So I need to presumably give some definitions of what contact manifolds are before moving on to. So the point of this talk is to define these equations and then show that you can actually construct moduli spaces for solutions of these instanton equations, which in some cases are quite surprising because a 5 manifold contact manifold could, even in the compact case, could be quite complicated objects. So the Reeb vector field could be very wild, about be a wild foliation. You can still make sense of this moduli space, show that it's actually a smooth manifold. So it's quite a surprising fact. All right, so contact instantons. And these ones, I feel like since I'm not giving any non-commutative geometry in my talk, these actually arose in quantum physics, so at least this caters to half the title of this conference. So this is showed up well in various incarnations earlier on, but I guess in a paper by Zabzin and Yuan Shilian in just a couple of years ago, 2012. They were looking at trying to, so these days there's a supersymmetric localization method for computing exactly the full perturbative partition functions for some gauge theories. So of course the Nekrasov partition function is an important example. And these guys were trying to do something similar in 5 dimensions. So there's a 6-dimensional holy great superconformal field theory that in some reduction gives you 5-dimensional Yang-Mills. So this is a 5-dimensional Yang-Mills, but it's n equals 1 supersymmetry, and it's twisted with some additional transhamilton. So it's a very long action, so I won't even write it down. The point is, once you have n equals 1 supersymmetry, you can localize using supersymmetric localization, and it turns out that the partition function localizes onto solutions of the contact instanton equations. So that's the physics origin of this, but I'm not going to really make any remarks about what the... Yes, it is, yeah. I think it's something like, don't quote me on this, this is plus trace plus possibly other terms. Something. This might be completely wrong, but it's a messy expression. So obviously you need fermions to get supersymmetry, so there's enclosed terms. Oh, this is the eta, yeah. Eta is the contact form. Let me get to that in a. Oh, for this one? Possibly, yeah. I think so. Yep. Should be something of that form. Yeah. Okay. All right, so let me just give you well, yeah, so you want, like, the case I'm looking at now is, like, that one would be the contact case. You don't, okay, yeah. So, like, actually, the case I'm looking at, the contact and omega is, well, omega is eta, the contact one form is obviously nowhere vanishing.
The answer is not in the first part. Yeah, but this is in more dimensions. So star F is not a 2-4. And then with omega,
Yeah.
which is closed, then we can not use umbrella, but phenomenon.
All right, so let me just give you a quick overview of what a contact manifold is so that we can actually write down these instanton equations. And then I'm realizing how fast time is going, so try to get to give you some information about the moduli space of solutions to these. So, okay, so a contact manifold, so it's an odd dimensional manifold. It's the odd variant of symplectic manifolds. So you have a eta in that expression. There is a one form. It's a contact one from your manifold, and it has the property that the kernel defines the distribution, the subbundle who's maximally non-integrable. So, in other words, this is a nowhere vanishing form. And you have a 2n-dimensional subbundle of your tangent bundle is contract distribution, and it has the property that d of eta restricted to this subbundle is a symplectic form. Okay. And in addition, once you have a contact structure, you have a unique vector field. This is gives you rank 2n rank. The 2n-dimensional subbundle is a 1-dimensional subbundle left, right, line bundle generated by a vector field. The unique vector field satisfying property that it pairs to 1 with the contact form and d. Sure. And your d eta vanishes on. Maybe too much. All right, so, and then you have your tangent bundle splits into these generated by this vector field. All right, so in other words, you have a GLN plus GL2n plus 1 structure, and the contact form is a reduction to a symplectic SP2n. So that's another way of saying this. And then we also want a metric structure because we want to have a Hodge operator, right? So contact metric manifold is that you have a compatible Riemannian metric on your manifold. So it's a Riemannian metric such that it gives an orthogonal decomposition, and the restriction of the metric to the horizontal distribution is defines Hermitian metric, and this is the eta restricted to H should be its Hermitian form. Okay. Sorry, I'm not writing everything out, otherwise it would be talk on contact geometry, contact instantons. Okay, so now I need one more condition to get a nice moduli space, and that's the notion of K contact. So we say that one of these are contact metric manifold is K contact if the metric is if the Reeb vector is a killing vector. And this turns out to be important also for that supersymmetric field theory I mentioned. To get a full supersymmetry for that action that I didn't write out, you actually need this K contact condition. Right? Contact if the Reeb vector field generates ax bisometries. All right. All right, so we're almost at the position of writing out this, the contact instanton equation. So let's, I'll walk you up. So we have differential forms on M, and these naturally decompose into horizontal forms, very similar to Gianni's talk this morning, although we have the notion of basic, horizontal, and basics. We have this action by the Reeb vector field, where we have, I mean, it's a splitting of a bundle. Okay, so the differential forms naturally split this way, and by omega h, I just mean form is valued in the valued in sections of sections along the horizontal distribution. All right, so now in 5 dimensions, this is in general, in 5 dimensions, the contact distribution is 4-dimensional. So we can make sense of the instanton equations in the transverse direction. That's the whole point. So the contact instantons is simply, in fact, it's precisely the same equation there, but the omega is now this contact 1 form. So this is the equation we're interested in. And in particular, it's a 5-dimensional, exactly. It's not, sorry, I should say, not pick M to be 2. So N 2 from now. So yes, so you put a G bundle on your 5 manifold, yeah, and then put a connection on it, and then, so actually this is an important point. So you can do 2 things. You can either start with a 5 manifold, a contact manifold, where you have this kind of foliation, 1-dimensional foliation, where you put a G bundle on it, and then you can talk about any connection such that it satisfies this equation. Or what you could do is you could pick a transverse structure on the G bundle, and then say, look at solutions, and then within the space of basic connections. So that's the difference. What we do is that we don't pick a basic connection. So it's a non-trivial result that infinitesimally, is going to look at the moduli space local structure. Any deformation is basic. We have to prove that. That's not given at all. So in particular, Tien's approach, where he was assuming omega is a closed form, he was assuming that he lifted the foliation to the G bundle and worked only along basic connections. So we don't do that. And just one remark is that you said we have 2 signs here. It turns out the anti-self dual corresponds to negative -1. Anti-self dual contact instantons are Young-Mills. You see that by differentiating, remember you get something like that. D eta, in our case omega is eta, d eta is a self-dual form. Fa is an anti-self-dual curvature, so they wedge to 0. So neither of them is 0, but they live in orthogonal complements. But not the self-dual ones in general. In fact, the contact structure gives you this distinguishing orientation in manifold. So in this case, there's no symmetry between just flipping the sign of the orientation. You get generally different behavior for the self-dual and anti-self-dual. But you can push the theory through for both of them. So you can work simultaneously, but just have to keep track of the differences. All right, so I want to say a few words about the manifolds we're working on, and then move on to actually say something about the moduli space and the dimensions. So first of all, I'm going to work on 5-dimensional compact K-contact manifold, 5 manifold. And you can already immediately distinguish 2 classes of such manifolds. So in one case, we say that such manifolds are quasi-regular. And this corresponds to the orbits of the this the Reeb vector field are all closed. So Reeb orbits all closed. And in this case, any such manifold is a Seifert vibration over symplectic orbifold. So this is just about this kind of manifolds that we're working over. Is a Seifert. So it's a symplectic orbifold with a orbifold line bundle, a circle bundle on it. So Seifert vibration. And X is a symplectic orbifold. And now in this case, you can immediately say something about the moduli space. If you have an instanton on this 4-dimensional manifold, you get a contact instanton by simply pulling back. So essentially, every solution is a pullback. Not in general. Solutions by pulling back ordinary instantons on X. Not every instanton in the quasi-regular case will do that form. So you can just take the length space over a CP2, and then take any flat connection. You can show that any flat connection is a contact instanton, so it's not a pullback. Or take a trivial circle bundle on a 4-manifold and take D plus the contact 1 form. Again, it's flat, but it's not a pullback. If essentially modulo these flat solutions, it's everything comes up. So if you just knew that if these were the only 5 manifolds, you would stop doing research immediately, because the moduli space is essentially the 4-dimensional moduli space, Donaldson. So there's nothing to do. But the rescue comes because this is not this case doesn't always happen. So we have if it's not quasi-regular, it's called irregular. And in this case, there is no 4-dimensional manifold to pull back from. So in this case, the closure corresponds to the orbit of the Reeb vector field is a torus inside the group of isometries of rank bigger than 1. So in this case, the rank is 1, so this circle action generated by the Reeb vector field is acting locally freely. So if it's free, it's a circle bundle. If it's locally free, it's some orbifold circle bundle. But in the irregular case, the closure of the Reeb orbits are tori of rank bigger than 1, strictly bigger than 1. In fact, you can show that it's strictly bigger than 1 and less than equal to 3. So that's the max dimension. There's a general result that on any 2n plus 1 dimensional manifold, the rank of this torus generated as a subgroup inside the isometry group is of dimension, is a torus of dimension maximum n plus 1. So in this case, it's n is 2, so you get at most 3. So either 2 or 3, that's the rank of this. And one class of irregular compact K-contact manifolds was generated by just a couple of years ago by physicists. These are called the YPQ spaces. So example, called YPQ. These are, as manifolds, they're diffeomorphic to S2 cross S3, but they're toric Sasaki-Einstein. Such that the rank of this, the closure of the Reeb orbit is 2, with rank R equals 2. So this is their irregular for suitable values for P and Q. Okay. So the point I'm trying to make is that these manifolds exist: the compact K-contact, and even richer geometry have a Sasaki-Einstein structure. So that's just a fact about K-contact 5 manifolds, and in particular motivates the investigations of these equations, because now you have actual genuinely 5 manifolds that do not have a 4-dimensional base. So you can actually construct try to construct a moduli space of those, and again, under suitable assumptions, these moduli spaces are smooth. And in particular, in the YP case, case, you can compute the dimension of the moduli space. Yeah, okay, I'm bad at this. My board technique is not as good as previous speakers, but right. Any questions at this point? Okay. All right. So in the remaining time, I just want to say, yep. Yeah. Yeah, so it's a so the Reeb, so the leaf space would be, it's the orbit of the closure of the leaves would be three dimension on which the 2-dimension torus acts. Yeah. And when you quotient out, that would prove it. But it's, but the Reeb orbits just generically they're not closed. You have the closure is just, it's only the quasi-regular case that are closed. In fact, that's the famous Weinstein conjecture in general for contact manifolds, where the Reeb orbits are closed. But this is a K-contact case. You know exactly when it happens. You can distinguish the 2 cases. Okay, so what I want to do now is to actually construct a moduli space of solutions for these. So, and I just want to say something about the local structure. So we just want to see where are they manifolds in the first place, and if they're manifolds, we'll compute the dimension. So local structure of the moduli space. Okay, so the idea is the moduli space is the usual thing. You take solutions, modular gauge transformations, and then you, it's very similar to the 4-dimensional case. You want this to be a manifold, so you topologize in some suitable Sobolev sense. So this is a Hilbert manifold. Well, Hilbert space. Well, I'm writing a Hilbert manifold. A priori, it's not a manifold because we have to check that you don't generically get singularities. You have to restrict irreducible connections, etc. But let me write it like this. We'll show in some cases it is a manifold, and the local structure is studied using deformation theory along Atiyah, Hitchens, Singer. So the idea is to construct a deformation complex for our instantons. So in other words, the formal tangent space at the point at say, A being a solution to either the self-dual or anti-self-dual instanton equations is described as by a DGLA. So these are infinitesimal deformations of your instanton modulo trivial deformations generated by the gauge transformations. Gauge transformation, exactly, the algebra. So you have some deformation complex. So I guess for those of you familiar with this story, how you construct moduli spaces, this is, I won't give you too much details. For those of you who aren't interested or haven't studied it, it's too little time, so I'll probably give you a headache. So at some point, I'll try to just emphasize the differences. At least we might appreciate that there's some work to be done. But then maybe this storyline will be a little bit obscure the way I'm explaining it. It's out of lack of time. Okay, so the idea is that you have a DGLA describing the deformations of an instanton. So you have instantons, and then you add any solution that you add, any element in here will give you another instantons if it's a solution to the Murray-Cartan equation, right? And then in our case, that naively you would write this complex. just doing the 4-dimensional case, you have infinitesimal gauge transformations. GP is the adjoint bundle. You have DA mapping into connection forms, and then you would write something like this: gauge fix, and look at the linearization of the instanton equations. So this gives you H plus like some okay. So this is how you start play the game in the 4-dimensional case. You look at this complex. This is not elliptic. Just do dimension count. You see that's problems. Not an elliptic complex. The idea is that the index of this associated Dirac operator gives you the dimension, the formal dimension of the moduli space, which is the dimension of the tangent space, which is the dimension of the moduli space. But this is not an elliptic complex, so there's no index. And even if it was elliptic, we're on an odd dimension of manifold, so the index is 0. So it is useless if you want to compute the dimension of the moduli space. So not elliptic, even if elliptic, the index would be 0. So it's not useful. So you have to do a bit more work to access the dimension. So in other words, you can make it elliptic by adding appropriate terms here. So you just need to add one more term here to fix the dimension problem, and one more term to get a full elliptic complex. But then again, that complex would not be useful for computing the dimension of the moduli space. So you need to consider different DGLA, and you note that our tangent bundle TM up there splits into horizontal distribution and the vertical distribution generated by the Reeb vector field. Using that decomposition, you get a bi grading on forms, right? You get along the horizontal direction and vertical. It's like if you've done jet bundles, you typically get two differentials going in different directions. So something similar happens here. So you get the following thing here. Let me skip writing out all the M's. So these are all valued in the horizontal distribution, and similarly here. And then along the vertical distribution, you get differentials going up like this. BV. So this is natural DGLA you get from split. Exactly. So let me just write. So this has the property that these differentials commute, and anyway, you can write out explicitly what these are, but it won't enlighten you probably. But the remark there is important. So this is again one situation where you get a very different behavior in the self-dual anti-self-dual case. In the anti-self-dual case, you get wedging with the symplectic form on the horizontal along the horizontal distribution. So this obviously in the real, because it projects. Yep, in the self-dual case, this term is not here. So it makes the analysis much easier. In the anti-self-dual case, you have to do a bit more work. So what you can do now, you can define the basic deformation complex by defining it as as the kernel of these vertical differentials. So it's simply so you can check that since the differentials commute, if you restrict to the kernel, these DTs restrict to a differential on the kernels, okay? So you get a basic deformation complex. And this is the thing we want to compute the dimension. This is a let me drop the m's. The dB again is just the restriction of the horizontal differentials to the kernel. Okay, so now this is a complex. Again, it's not elliptic, but it's transversal elliptic. Okay, so this is a meaning that the symbol is not. The symbol is an isomorphism when restricted to the transverse direction. So this is transverse elliptic complex. And there's a general theorem that guarantees that these the cohomologies are all finite dimensional. So you know that you have a Fredholm property. Okay, and something else you can do, now we have a complex that is, hopefully is going to give us a dimension for the moduli space. Something else you can do is to construct a Giesen sequence. So using transverse Hodge theory, which again is a place where we need the K-contact structure. So if you don't have K-contact manifold, you don't necessarily have harmonic representatives for your cohomology. So this again uses the K-contact condition. It gives you a Giesen sequence relating the basic cohomology of that basic complex to the cohomology upstairs. Giesen sequence. And in particular, you have that using the Giesen sequence, you have that the basic cohomology is isomorphic to H1. So in other words, infinitesimal deformations are all infinitesimal. Locally, they're all basic. And in particular, this is the dimension we wanted that we couldn't use that complex upstairs to use. But now since we know that that's the same as the dimension of the basic cohomology, if we can compute that transverse index, that will give us the dimension of the moduli space. All right. Sorry? No, so you can show that the omega is injective on from H0 to H2. So yeah. Yeah, it just injects, yeah. Oops. Okay, so we have this result. So we're almost there. I just need to say, okay, so the idea is that this deformation complex gives you a coordinate chart around that instantons. You pick a solution, and then you have a general, the Kuranishi model for deformations give you a general theory for building a local chart. So let me just state that as a theorem. So there is an analytic obstruction map. takes an open subset of the origin in H1 into H2. So recall H1 is the infinitesimal deformations. H2 is abstraction to extending that to genuine deformation, right? So we really want this map phi to be 0. We want to kill off the abstraction to getting full deformation. So and there is a neighborhood of our contact instanton such that homeomorphic to so this is neighborhood of the origin. So you give you homomorphic to the inverse image of 0 mod the subgroup of constant gauge covariantly constant gauge transformation for this connection. Right? So these are automorphisms mod these are the automorphisms that gauge transformations that preserve this connection. So this is a covariantly constant gauge transformation, which in particular contains a center. So this theorem, just telling you, this gives you the general local structure around this instanton in the moduli space. So which is still quite hard to analyze because you need to know what this phi is to describe it. So what you really want to get a nice manifold, you want this to be a trivial map. So we say that the instanton is unobstructed if this abstraction map is 0, and also we say is irreducible. Irreducible connection if this gamma is just an identity group. So if these two hold, so we work with an irreducible connection, and this connection is unobstructed, the map phi is 0, then M is locally homomorphic to Euclidean space, RD. So it's literally a smooth manifold where D is the dimension of H1. So it's if you have those two things satisfied, then you have a genuinely smooth manifold at that point, locally. And you have a dimension you can compute from that complex. Okay. So in the remaining 10 minutes, let me just give you a theorem where, so once you have this in place, you want to make sure when can I make this phi go away. So you need some vanishing theorems. And let me just state one at least so you're convinced that we actually do get smooth manifolds in some cases. So if A is irreducible, before giving the vanishing there is one more important result, is that if A is irreducible and the basic H2 vanishes, that implies that phi is 0. And this is quite, it looks obvious, but if you look here, this is not the basic homology. The basic homology sits inside here. So if this goes away, if you impose vanishing conditions such that H2 of M goes away, then by the Giesen sequence, that implies that H1 has to be 0. And it's a 0-dimensional moduli space. So it's quite non-trivial. You have to actually sit down and show that it's enough that the basic H2 goes away. And that if it's a reducible instanton, it ensures the vanishing of the abstraction map. So again, this is not as trivial as it looks. And let me just give you one instance when this happens. Is if M is a compact Sasaki. So Sasaki condition is the analog of Kähler. So contact 5 manifold is Sasakian if its metric cone is a Kähler 6-dimensional Kähler manifold. So if you like, or transversely, you have a holomorphic in the foliated chart. You have holomorphic transition function. Holomorphic transition functions. So the 5 manifold with a positive scalar curvature. But so once you have a foliation, you can define transverse Levi-Civita connection, transverse curvature, etc. So, in fact, it's not difficult to show that the transverse scalar curvature is the usual scalar curvature upstairs on M plus 1. So. Then this basic homology group is trivial. So on any Sasakian 5 manifold compact 5 manifold, you get a smooth moduli space if the connection is irreducible. You can similarly show if the manifold has a transverse Calabi-Yau structure, that's also enough to kill off the basic degree 2 homology. So in this case, we get an honest, smooth manifold structure along the solution, and you can compute the dimension of the moduli space. So let me just end by giving you at least one example of what that dimension looks like. This is Right, so let me, before doing that, let me just say there's two notions of transverse out there. So there's a transverse to foliation, and then there's transverse to group action, which is what Atiyah developed the notion of transverse elliptic complex, transverse to a group action. And what that means is that you have a complex where you have a group acting on your space, and the complex might not be elliptic, but it's elliptic. The symbol complex is elliptic if you restrict it to the subspace of the tangent bundle that vanish along the orthogonal direction of the group action. So evaluated on vertical vector fields along the group action, it's trivial. In general, that's not a vector bundle, but it makes sense. You have a projection onto the base M, and for such transversely elliptic complexes, you can make sense of an index. So you have a group, you can take its equivariant index. The equivariant index is kernel minus co-kernel. These two spaces carry representations of your group. And if it's transverse elliptic, what it forces this, the property it forces upon this complex is that the kernels only carry finitely many multiplicities. And the growth rate of these multiplicities is such that the index becomes a distribution on the group. So the index, equivariant index, is not a character, it's in this completed distributional representation ring. But the point is, to compute the index, in our case, we need just the invariant part of that equivariant index. Meaning if you decompose it, it's just a multiplicity of the trivial representation. So you can actually, by reformulating this complex to be a complex relative to transverse to a group action, you can actually get numbers out. That's the point I'm trying to make here. And let me spare you the details of how you go from transverse to foliation to transverse to group action. Again, you need some conditions for that to work. But once you sit down and do that, you can actually get a dimension out. So let me just finish by giving you one example. The example I give you is a quasi-regular case, which, remember, is very closely related to the 4-dimensional case. But you can actually use orbifold index theory to get a nice formula out. So assuming that your manifold is, let me give you the formula, and then I'll explain what the different things are. So first of all, the first bit, those of you familiar with instanton moduli spaces. This is very similar to the usual case. You have a basic Poincare, first Poincare class of your bundle evaluated on the fundamental class, plus dimension of your group for your G bundle, and then 1 minus. So everything here is the Betty numbers are Betty numbers of the basic complex. Plus. So you get this expression, which if you drop the basic is the usual dimension for 4-dimensional instantons. But you also get, if it's a Sasakian, if the Sasakian 5 manifold, but it's quasi-regular, you have singularities, right? So the Reeb vector field doesn't act freely, only locally freely, so you get fixed points. And that will give you this additional expression. Minus. Anyway, minus. Let me just skip the details. That probably won't help you anyway. So you get this. So these additional terms come from the stabilizer groups for. So the base of your quasi 5 manifold is a symplectic orbifold, or in the Sasaki case, in the Keller orbifold. So, these weights come from the stabilizer groups for your orbifold. In particular, you can show that in a K-compact case, all the uniformizing groups of the orbifold has to be cyclic groups. So this MJs are the weights of, is the order of the cyclic group. And you can also, as I said, there's the interesting case for these moduli spaces is if you work on an irregular K-contact manifold, where you don't have a base, 4-dimensional base from which you can pull back instantons, because then you get generally 5-dimensional geometric objects. And the moduli space in that case is extremely difficult to compute. But if it's toric, you can use the moment map. The moment map is a polytope, so you can use the combinatorics to compute dimension in some cases. All right, so thanks for listening. I know this is too much details for afternoon class. You told me to tell you everything, so that's yeah. Sufficient. You just, yeah, it's just a sufficient condition that guarantees the vanishing of H2. Yeah, it's. I mean, if you could show that, I mean, then you know that there is no recipient for that map phi. If you can show that the map, it's very hard to analyze that map. If you can show this is 0, then you can have a, you know, you could map into something non-zero but still be 0. And let me just say something. This is just about the local structure. Of course, what we want to do with this is to get the invariance for a contact manifold. Right? So it's one thing just studying moduli space because you can, but I mean, already the 4-dimensional case is extremely hard to, you know, go through the compactification, etc. And it doesn't get any simpler doing it in 5 dimensions. But what you can do is, like with the benefit of hindsight, is to do Seiberg-Witten equations. And because you know the Seiberg-Witten equation in 4 dimensions is already compact moduli space. And you can do the same story for the Seiberg-Witten equations. And in that case, actually, you get Seiberg-Witten invariance for these 5 manifolds. And this is a work in progress, but hopefully you can show that if you have a 5 manifold, these invariants might give you abstractions to the existence of K-contact structure. Or if it's already K-contact, this might give you abstraction to them being Sasakian. So you can, so this is the hope of doing this business in the first place, is to get invariance from the moduli space to geometric, to the geometry as the 5 manifold. But yeah. Yeah. Okay, so this is something different. In the 4-dimensional case, the G bundle is just this. Is in 4 dimensions. It's just a Pontryagin class classifies the bundle, and then this we're talking about is that like you have this topological charge for the instantons, right? So in the 5-dimensional case, you have a notion of a basic Pontryagin class. They can take continuous values. It's not quantized. So you can, once you have a transverse G bundle, you can put basic connection, basic curvature, and then do Chern-Weil theory. So you get a basic Pontryagin class. But it lives in the basic homology, and you could get a non-trivial class even if the bundle is trivial, right? Because it senses a transfer structure. On that hand, the price is that it's not, it's a real class. So it's probably more complicated than that.